Hello and welcome to the webinar here at Glasgow Caledonian University, organized by the project Mainstreaming Innovation. My name is Branka Dimitrijević and I'll moderate today's webinar. I also direct the project Mainstreaming Innovation. Before we continue, just a few management points. If there is an alarm, fire alarm, we will have to stop, or if there are some interruptions in online connections, please do try to reconnect later. However, this webinar will be recorded, so video recording will be available in a few days. Just a few words about our project Mainstreaming Innovation. It is a joint project of 9 Scottish universities and its focus is on integration of low-carbon infrastructure systems in the built environment. We support collaboration between Scottish businesses and these universities in developing innovations for low-carbon infrastructure systems that connect landscape and biodiversity as a green infrastructure, then energy generation from renewables, energy efficiency of buildings, technologies for water saving, harvesting, waste management, low carbon transport, and of course information and communication technologies, or ICT, and their use in monitoring and management of these low carbon infrastructure systems. If you need any research input from academics of these 9 universities regarding applications that you might be preparing for the EU, UK or Scottish funding, please do contact me and I will connect you with researchers at these universities. So that is a brief introduction of our webinar on the future for electric storage heating. This is a webinar that will be presented by speakers and researchers of University of Strathclyde, and they are Katalin Svehla and Simon Gill. Welcome, and I would kindly ask you to start with your presentations.
Okay, thank you very much for inviting us to give this talk. You'll see that our version of this talk has a question mark after it. Does electric storage heating have a future? It is a very unfashionable topic at the moment, very 80s technology. Lots of storage heaters were introduced all over Europe when they were building nuclear power plants in the 1980s. And now they're all being ripped out again as fast as people can take it, because it was clunky, it was not so easy for the occupants to use, and the focus of modern technology has moved on to other things. However, given that the future world of renewables requires storage, and storage is the holy grail, I think it's been called in other areas, for making a green electricity grid function. And actually we've got a lot of distributed storage out there, although it's an old technology. It's proven, it's relatively cheap to install, and it's got a high energy storage density. So, question. Does it have a future? Can it have a future in a green grid world? So what we're here to talk to you about today is really a live example of, a live example of a smart grid working with electric storage heaters, modern advanced technology heaters, that is maybe a laboratory for exploring what can be done in the future with an unfashionable technology. This live laboratory is in the Shetland Islands, offshore UK, and the project is underway just now. It's got a number of partners who have worked to develop the technology and roll it out, led by Scottish and Southern Energy, who are the distribution network operator in Shetland. They worked together with a number of companies, principally Dimplex, who developed and manufactured the advanced heaters, with Smarter Grids Solutions, who is a small company who have been developing the advanced control systems necessary to make it all work together. Very importantly, we've had Hjaltland Housing Association, which is controls a large number of social houses in Shetland, and their active participation in this has been very important from the point of view of getting the people whose houses this technology will be involved in on board. And last, but we hope by no means least, the University of Strathclyde has been a research partner in this project. So we've been there monitoring and doing simulation studies on how the technology will work. So our presentation will be in sort of 5 parts from this. We'll give you a little bit of a flavour from the manufacturer's perspective. You know, why did Glendimplex invest a lot of time and money in developing advanced heaters? Secondly, what is about the network operator? Why do they think this is a good technology? What does it look like from the point of view of the occupants from Shetland? And then finally, we'll talk about 2 aspects of the how it's worked in practice, how the system has performed. One from the point of view of the occupants in the houses, and the second from the point of view of the grid. And my colleague Simon and I will be swapping as we go along to tell you this story. Okay. So the first part is what's in it for the heater manufacturer. Glendimplex is a very large company manufacturing heaters of all kinds with a base in Ireland. And when they started looking at the future of the grid in Ireland, and then beyond that the future of the grid in Europe, they started to see various things. And one of them is that the roadmap going forwards has a significant amount of electricity being used for heating and for transport, which it wasn't before, so more or less doubling over the next 30-40 years. And so that means a large increase in the amount of electricity required to fulfill the demand. And then the second thing that's going to happen is that the proportion of that electricity will have to be that is produced from renewables will need to grow quite significantly to at least 50% and possibly even over 90%. So in order to make that happen, a lot of things need to be put in place, because we're certainly not there now. And there is a great deal of work at every level, from European down to sort of individual network level, around how do we make the transition from where we are now to a smart grid enabled world where there is all the systems are interconnected, everything is flexible, everything can be changed very quickly, and where there's a lot of storage and distributed storage. And although I don't think Glendimplex would claim that they're going to solve the whole smart grid problem for Europe, they see distributed heat storage and flexible demand as a key component of the end solution. And they look at it from the point of view of what's happened to telecommunications technology over the last 25 years. Certainly when I was going to university, we had fixed telephones. It was a single centrally controlled system, and the telephone at the end depended on sort of everything happening in the middle, in the centre, to work correctly. Today, we just expect telecommunications to be there everywhere and at all sorts of levels in our day-to-day lives. We expect two-way data flows, not just one-way. And this has happened quite quickly, in fact. So looking at that kind of model, we would see a world of, in power systems, where the old model of large central generation and sort of fairly dumb wires that then distribute the centrally generated energy out to users, being replaced by a world of prosumers. Not very keen on the word, but it probably is a good description of a life where, you know, you might in your house have some solar panels, you might have a smart car charging, electric car charging in the system, you might have fridges that communicate with to and from the central network, turning on and off to help balance demand and supply. So that world, yes, it will be a change. but it may happen faster than we think possible right now. So, what's the Glendimplex's contribution to this world? And it's smart electric thermal storage. And they have electric storage heaters, space heaters, and also hot water tanks, which, let's not forget, is also a form of electric storage heating. What's different about these heaters relative to the old-fashioned ones that people are used to using? 4 levels, really. The first of them is to do with the quality of insulation. And the new heaters use technology that's used in the space station for making sure that these things are really heat stores and not heat sieves. So there has been a good step change in the ability of these heaters to retain the heat that's put into them, and then allow the occupants of the houses the flexibility to take that heat out when they want it using occupant controls. The second sort of layer of innovation, and this is why they call them quantum heaters, is that everything is discretized. So the heaters are capable of taking in power at several different levels, fixed but varying levels. 3 in the case of the space heaters, and 7 in the case of the water tanks. And they're capable of varying the level of power input at 15-minute intervals. So they can be controlled to a degree of granularity that was just never possible before. The third thing that they can do, and this is the smart bit, is that they can communicate with the outer world. So they can operate independently if they need to, but they can also be linked to a communication system that allows them to take in instructions from the outside, these 96 steps for the day ahead, for the charging levels. And they can communicate back to the centre to tell them what their storage level is at any time, so that a central operator can really know where and when to sort of route power on signals. And the fourth level, which gets into what I would consider the very smart area, is that they have a capability to respond automatically to sudden changes in grid frequency. And this is another very important aspect from the point of view of managing a grid with a lot of renewables on it, which Simon will talk about more later on. But they are capable of turning on when when they sense through the changes in frequency that that there's too much power coming into the grid, or they can turn off automatically if there's suddenly a drop. And these sort of events happen over a scale of seconds and small numbers of minutes, so that does not really interfere with their ability to respond to charging on and off commands. But it's a hugely helpful facility. How am I doing for time? Okay. This next slide is just a quick overview of, from the point of view of Ireland, why this technology could be really helpful. The grey band shows renewable energy production profile over the year, month by month. The green part of the chart shows potentially the space heating requirement, and you can see that there's more space heating requirement in the winter when there is more wind and therefore more renewable energy production. But also there is an element of hot water demand for the water heaters, which it goes on all year, and so the smart heaters will perform both in the winter and the summer, and a little bit matched to the profile of demand. Okay, so this is what the heaters themselves look like. They're quite sort of smart and elegant looking, and they have a whole slew of user set controls. They can be set just like a normal central heating system. Finally, looking broadly at the European level, there are an enormous number of existing dumb electric storage heaters out there. And if they were all to be replaced with smart heaters, you would get storage capacity in the sort of multi-gigawatt hours magnitude. Sorry. So it's a technology that has a potential that is way beyond what this laboratory gives. I'll hand over to Simon to talk now about the point of view of the network operator.
Thanks, Kathy. My name's Simon Gill, and I'm a member of the Electronic and Electrical Engineering Department at Strathclyde. So this has been a really good project for me to work on with Kathy, representing the mechanical engineering department. It's really good because it brings together two sort of areas of energy generation, transmission on the electrical side, and usage on Kathy's side. And it really is important to consider both sides of that equation when we look at future energy systems. I've got two sections to do in this presentation. So first, I'm going to give you a very brief overview of the Shetland situation and why this project is being rolled out on Shetland in the first place. Shetland's quite unique and has some unique issues in terms of the power system. Then when I come back for the second part of my presentation, I will talk about some of the modelling we've done and try and draw out some of the issues which are maybe relevant to UK operation and general power system operation, not so specific to Shetland. Okay, so I'm speaking over these slides in the first part, which have been provided by Scottish and Southern Energy Power Distribution. They're the company that operates the network on Shetland. They own the wires, the overhead lines, the transformers, all the parts of the network. And just one thing to be careful with when you're thinking about this, that despite the name and the logo, that's not the same organisation as the supply company SSE that you may or may not buy electricity from. They are part of the same group, but they are a regulated part of the group, and they're not allowed to kind of give preference to SSE as a supply company. They have to work fairly with all supply companies. They own the infrastructure, basically. So, let's move on. Okay, so just a bit of an introduction to Shetland. It's 130 miles north of the UK mainland, right out there in the sea. Very windy place. I've been a couple of times and been blown over a couple of times. It's an isolated electricity network. By that I mean it's not connected to the UK mainland. Operating a power system involves second by second balancing the generation of electricity and the demand of electricity. If you get those two things out of balance, even by a small amount, you start to lead to instability in the network. And so there's lots of things which are put in place to try to balance those two things in real time. And on Shetland, because it's such a small system, any imbalance can very quickly lead to quite serious consequences in terms of demand getting cut off and experiencing power cuts, generators reaching their limit in terms of the frequency with which they can operate and cutting out. So on Shetland, the task of maintaining that balance is kind of brought into sharper relief, maybe, than it is on mainland UK. And that's one of the real reasons for bringing this together. In terms of electric storage heating, there's no gas supply on Shetland. And as such, at the moment, the majority of houses on Shetland are either heated through electricity. There may be some heated by oil in their own oil tanks, and there's quite a few that are just heated via solid fuel systems. So providing a cheap form of heating to somewhere without gas is really quite important. The main power station on Shetland in Lerwick, the capital, is quite old. It needs to be replaced quite soon. It runs on diesel, and because it's old, you have to be careful how you operate it. There is also generation from Sullom oil terminal, which have their own gas supply internal to the site, and they generate electricity which they sell onto the Shetland network. But there's a complex power purchase agreement there, and that has to be managed as well. There's environmental issues. So the Lerwick power station has had an extension on its life, but needs to be replaced because of more stringent emissions limits at the moment. And for all these reasons, despite the fact that it's so windy on Shetland, there's been no new wind connections for quite a long time. Shetland has 4 megawatts of wind generation, mainly all in one place, Borrowdale Wind Farm. And it has the highest capacity factor of any wind farm in Europe, I mean possibly in the world. Some years its capacity factor exceeds 50%. Compare that with the UK national average of about 25%, and you can see why it would be good to have more wind connected on Shetland. Shetlanders themselves, I think, are kind of keen on the idea of wind generation to supply their own energy needs. And so it's a project which has support on the islands, particularly when it's linked to electric storage heating, for example. The project we're working on is called the Northern Isles New Energy Solutions Project, and it comes in 2 phases. Firstly is the rollout of a trial phase, and that's what we're doing at the moment. That's to install electric storage heating in an initial estate of around 250 houses, to integrate a new wind generation and to manage that in real time, and I'll just mention what that means in a second. And then the second phase is to repower Lerwick Power Station, build a new power station which meets the emission requirements and the environmental limits that are set today, but with all the infrastructure that the Nines project brings, there's the possibility of either reducing the size of that power station that you have to build, or reducing the quantity of electricity generated from that power station, therefore reducing how much fossil fuel electricity is used on Shetland. Now, because of all these limits, you have to actually manage generation in real time. So if you add more wind generation, you make the stability issues to do with frequency that I mentioned earlier slightly more complicated, and you put the system at more risk of failure, of faults, etc. And so what you do is you look at the real-time conditions, how much wind there is connected to the network, how windy it is, how much output it's doing at the moment. You look at how much demand is online, how much frequency responsive demand is online, what units are being used at Lerwick Power Station, and you decide at the moment we can fit, for example, 15 megawatts of wind generation. Now, if wind is trying to generate at 18 megawatts, you then tell certain wind generators they have to reduce their output at the moment. And that real-time monitoring and control is known as active network management. So just to link that to the diagram just here, you've got 3 generation stations, Lerwick Power Station, Sullom Terminal and the wind farm, connected to an active network management scheme. The idea is to bring new small wind, maybe turbines connected at village halls for example, new large wind, which can either be commercial wind farms or again community owned wind farms but slightly bigger ones, to connect houses through the domestic demand side management project, and to link some other things in, large scale chemical batteries and a large scale electric boiler and thermal store potentially linked to a district heating network. Now, what you can see here on this slide is an indication of the demand levels for electricity across the year in Shetland. The blue line at the top shows you the maximum demand for electricity each day, and the red line at the bottom shows you the minimum demand for electricity each day. So across the whole year, demand for electricity goes from approximately 11 megawatts up to approximately just under 50 megawatts. So it's quite a broad range, and you need to be able to manage that. So I mean, if you didn't manage wind generation at all, you could never fit more than 11 megawatts on, because at certain times that's as much demand as there is. So at those times you'd need to turn wind generation off. Now actually you can't even get anywhere near that, so you have to bring wind right down to approximately 4 megawatts. But over here, when you have a lot more, I need to move the pointer. Over here where you have a lot more demand, you can fit a lot more wind on. This slide just shows you a little bit about how you can smooth demand. So the best you can do is to completely flatten the electrical demand profile across a day, so that it's just at one value all day, and then you deliver the same quantity of electricity in a much more even manner across the day. So that's the kind of, so on this particular day when the maximum demand is approximately 46 megawatts, you could bring that down to maybe 37 megawatts. Okay, so that's to do with the sizing of the power station that you need, because you therefore need maybe a slightly smaller power station. So this is about managing peak demand and managing the ability of wind generation to connect. The final slide, I think, from me just now is just to summarise those things I've said. Currently we've got 3.6 megawatts of wind generation at Borrowdale, plus about an extra 400 kilowatts spread across the islands in small local groups. But that wants to be increased, and the objective is to try and get maybe to get up to about 12 to 14 megawatts of new wind generation to connect. That would allow the percentage of Shetland's electricity generated from wind to rise from about 7% up to about 20%, which is a significant improvement. So I'll pass you back to Katy, and when I come back I'll talk a little bit more generally about power systems and some of the modelling we've done.
So the final perspective from the different partners that we wanted to bring you was why are the Shetland Housing Association interested in doing this project, and what have the occupants actually found during the trial? What's it really like to live with the new technology? Shetland is the main independent housing agency in Shetland. They have over 620 sort of affordable homes, social housing, and they are actively engaged in trying to manage fuel poverty and reduce the energy consumption in those houses. So they've already had quite a lot of experience in sort of trying to bring down total heating demand, and they were sort of quite keen on participating in this project because they saw it as a means for improving the energy consumption for their occupants. And they knew the occupants, they know the houses, they knew the occupants, and they provided a friendly face. So it wasn't the nasty big electricity company who was coming to talk them into something, but somebody that they knew and trusted, and there was a representative, a nominated person all the way through the trial who they could turn to, who was part of the housing association, and whose job it was to make sure that issues were flagged very quickly and dealt with. So that was proved to be a very good means of managing customer engagement. So that's all the really positive side of it. One sort of potential issue around Katalin involvement is that they tend to own the newer houses in the island. Now, in Scotland, if you look at the bottom left-hand picture on this slide, that's a fairly typical kind of house as built in Scotland. They're timber kit, so-called, so they've got a timber frame, maybe block and render outside, and a substantial proportion of both Shetland's and Scotland's stock was built quite early on with very little insulation in the walls. Kjaltland's estate was mostly built after 1990, and therefore we're already starting with a group of houses that are better insulated than most. And they have a fairly significant proportion that are built to sort of Swedish and therefore even more highly insulated standards. And all of their properties had double glazing and substantial roof insulation installed. So they have done all of the easy things to sort of lower the energy use. Sorry, what have I done? I've lost the screen. If somebody can bring that back, but can you move to the next slide? Sorry. Okay.
No problem, that will be fine.
Right. So, right. Do I just keep on because
We see the slide benefits of HHA.
yeah, okay. So for the housing association,
we can
for the
continue.
housing association, when they came to upgrade the existing old electric storage heaters, this was a good way for them to give the customer something better for relatively little extra costs. The new system helps towards the energy rating, the SAP energy rating of the houses. So they're sort of trying to future-proof these homes. And as an association, they want to be seen as forward-thinking and green. So again, these were all reasons why they were keen to participate in the project. So in 2011, they installed heating systems in 6 trial houses, and this equipment was installed with a lot of monitoring around it, so that we could see how it would work in practice, and it would inform the approach for the wider rollout. You'll see in the picture in this slide, that's the size of the intelligent communications box that was put into the houses to allow the smart part of this system to be trialled. So it wasn't particularly intrusive. Again, the houses they picked, 6 of them were these Swedish timber houses, which were very heavily insulated. So 5 were, and the 6th one was a converted building of a traditional thick stone construction. So they did tend to be, even within Kjaltland's own properties, some of the better insulated buildings. So the trial was going all the way through 2012 and into 2013, and then the full rollout using the production versions of the heaters. So Glen Dimplex updated the functionality based on the outcomes of the trials, and the installation to 237 properties began in September 2013, and it'll finish at the end of this year. So far, it's all been going quite positively. Hjaltland and SSE have expended quite a lot of time and energy in communicating with the tenants and in training them how to use the controls in the new system, because of course, the effectiveness with which they work does depend a little bit on how they're being used. The tenants have to give their consent to taking part in the sort of remote control of their heating, but so far, based on the trials and based on the communications, they have nearly all said yes, and they think it's a good idea. There have been, the association has to manage the practicalities of the rollout, like getting into properties and making sure that the installations are done in a sort of manner that doesn't disrupt the life of the tenants too much. And a final challenge, which was just to do with timing, was that when the new heaters started to come on, coincided with the time when electricity prices in general were rising. So although in reality the energy use might be going down, the bills were not. And that takes quite a lot of sort of discussion and communication to sort of manage perceptions around that. But yeah, that's just timing. The kind of typical feedback that they've had through this nominated housing officer. The heaters are really good. It's instant heat when you need it. The houses are warm, but the heaters are not dangerously hot anymore. They're not as hot to the touch as previous storage heaters. So these are all pointers that say that the technology is working as it was designed to from the point of view of the tenants. Okay, so the work that we've been doing in the Energy Systems Research Unit in Strathclyde University has been to monitor data about what's been happening in people's houses, so that there's some quantification as well as how people feel about it, to test the performance of the heaters. And I said that the prototypes had had a lot of monitoring equipment built into them, and this slide sort of starts to describe the level of monitoring. So there were each heater is individually equipped to measure every element of energy that's coming into the heater, energy that's leaving the heater, and the level of storage in between. And on top of that, there are measurements being made of temperatures, room temperatures, thermostat settings, outdoor temperatures. So there's a huge amount of data coming in around the performance of each heater. The same sort of monitoring is happening on the hot water tanks as well. So there were 13 heaters in the 6-house trial. Each of them had between 12 and 14 data channels. The data was being collected between 1 and 5 minute frequency. So actually the first part of the problem was dealing with the quantity of data you were getting. There's almost more there than you could assimilate. So that is a great resource, the monitoring outcomes. We have had challenges there because Shetland is, as well as being isolated from the mainland in terms of grid, it's also out there on its own when it comes to telecommunications. So we've had to deal with a lot of comms outages, especially during the trial. So the challenge was a lot of data, but not an awful lot of very long-term continuous data. So what were the outcomes of that data? What do they look like? First of all, how was it for the occupants? The table in the top left here shows the difference before and after installation of the new heaters in living room temperatures. So it's the average temperatures in the winter before and average temperatures in the winter during which we had monitoring data after the heaters were installed. And what we see in the 6 houses is that the 3 who were previously much warmer than average have now got a cooler temperature. The 3 that were cooler than average have now got a warmer average temperature. So there's been convergence in living room temperatures to something that is actually considered to be a very comfortable, neither too hot nor too cold winter living room temperatures. And that's a good indication that these heaters are more controllable, that they're not leaking heat in the way that the previous versions were. Moving to the second, the pair of charts that you see, these charts show how much heat was output from 2 of the living room heaters in 2 of the flats. The pink represents the quantity of heat in any one week that came from the fan-assisted output, so therefore the occupant-controlled output. And the yellow represents the amount of heat that was output sort of passively through, even though the heaters are very well insulated, they still do leak some heat. And the differences don't look too much at the differences in the size of the bars from week to week, because that is constrained by the amount of data that we could collect from week to week. The thing to look at is the difference in any one bar between the yellow and the pink area. And you'll see that in the bottom chart, nearly all the heat output from that particular living room heater came through the uncontrolled passive output of the heater. On the top right hand, it's a different house, a different family. They like to keep the temperatures warmer, and therefore the percentage of fan-assisted output was quite high. But these heaters still will output between 120 and 240 watts at the sort of level of fill that they were doing in the trial. And because these were exceptionally well insulated houses, they didn't really need the fan at all. And in fact, the smallest property by far, which was the converted stone flat, made the greatest use of the fan. Okay. So the second side of this was, how do these things perform from the point of view of the network operator? Now, during the trial, of course, these things were not actually connected into the central control system. They were connected into something that mimicked that. But still, how does the total performance work for the network? And the first thing we saw was that the heaters rarely ever use more than 40% of their storage capacity. The bar charts show each heater, each of the 13 heaters. The dark purple bands show the range of fill of each heater, that represents 95% of the operational time. And then there's a paler purple bar that shows the last 5%, the sort of the excursions into the last 5%. The black bars at the side show what the total, the net effect of all the 13 heaters are in terms of storage capacity, because of course the things are not moving up and down in sync. So there's a big diversification effect. So from the point of view of the network operator, there is a good 40% of the total storage capacity is there that could potentially be used without interfering in the energy demand of the users. That was the good news. The not so good news was that all of the heaters had a significant proportion of their power was taken outside of the schedule when they were being instructed to charge. So there was high unscheduled draw, and there was also a commensurately high amount of scheduled power that was not drawn. The two pairs of the two paired charts at the bottom show how much unscheduled draw, scheduled draw, and scheduled power not drawn there was in just one of the heaters, week by week. And the left-hand chart shows in terms of the amount of time when this was happening, and the right-hand chart shows the amount of energy that was being delivered. Green, unscheduled; yellow is scheduled, not drawn. The brown bars show when it was actually charging on schedule. And when we started to look into what was going on to make this happen, there were quite a lot of different independent reasons. Some of them were to do with system level settings, which then could be changed and improved on later on. So for example, the scheduled energy wasn't particularly linked into the actual energy demand of the house. So two houses would have the same schedule, even though one might require 50% more heat than the other. So of course they were going to behave differently. But there was another suite of issues which was to do with how the occupants actually used their controls. And almost it seemed like these heaters are just too smart for their own good, because they'll estimate the amount of energy required for the next day. But if the occupant, based on thermostat settings, but the occupants would use the thermostat settings to turn the heater on and off. So they turn it up to get some more heat, they turn the thermostat down to get less heat. This confused the smart controller, and so on. So this one, I think, is going to be the most challenging to sort of get right in the operational system. However, I'd say there was a lot of learning that came out of this that went into the design of the production versions of the heaters. So because the heaters are working in real houses with real people, there's a limit to how much experimentation you can do of that there. So, and you can't change the timings or the tariffs without going through an awful lot of steps. However, with good quality thermal simulations, you can do a lot of experiments and what-if scenarios just to see what might work and what might not work. And that would help to back up any sort of real-life changes that you might want to get permission to do. So the next step that we carried out was to build some detailed simulation models of the houses and of the individual heaters. And this is using a program called ESPR, which is a sort of dynamic, non-linear, interactive program that can model each heat transfer process that's going on in a house individually and monitor their interactions. Houses were modelled with a high level of internal detail because the demand on the heaters would depend on where the heaters were, which rooms and what size. So you had to model it room by room. The heaters themselves were modelled in a lot of detail so that each step of the heat transfer between the electric charge in the heating element passing into the core and passing out of the core through either conduction through the walls and the passive output, and the fan assisted output, which was through an airflow through the core. So each of those processes could be modelled separately, and so the separate discrete power inputs could be modelled, and the internal controls and the external controls could be modelled separately. And we finally calibrated those models against both laboratory data and field data. And on this slide you'll see the agreement over a 3-day period between the room temperatures in the simulation, which is in red, against the room temperatures that were actually measured in the field. So we think that these models really are a good tool for doing more exciting trials of operational processes. So then we went to look at just how sensitive are these houses to different schedules. And we looked at several different approaches to charge scheduling. So we looked at changing the timing of the energy delivery into the houses, and we modelled the standard, the default scheduling, which is teleswitching, which is what most storage heaters around the world operate on. There's a sort of certain tariff hours during which the heaters charge if they can, and then they switch off when they're full. We also looked at what happens if you deliver exactly how much energy the house is going to demand each day. Exactly. Then we looked at, and if you don't get that quite right, you might be storing a little bit of wind from one day to the next. So we've got sort of not quite exact demand daily charging. And then finally we also looked at a scenario which we called high wind storage, which is that you would plan to deliver up to twice the day's demand on a day when there was a lot of wind, and you would plan to deliver nothing at all if you could, if it was low wind. So that was energy delivery approaches. We also looked at what happens, is there a difference depending on whether you charge it early in the morning, in the middle of the day, or late at night. We looked at what happens if your charging is at the lowest power level over a long period versus at high power level over a short period. And we also looked at 2 of the houses that were in the trial, an insulated timber house and a stone retrofit. And we also looked, although we didn't have the monitoring data for that, but we also modelled an older, leakier, less well insulated house as well. So we did 3 houses, and there were 16 different schedules applied to each house. This first slide shows the outcome of those studies. in one of the houses on the living room temperatures. And each band shows a different schedule, and the colours represent 20 percentile intervals. Again, this is over time during occupied hours only, what the living room temperature was like. And apart from teleswitching, where the living room temperatures were considerably above the set point, just simply because the heaters would charge when they had capacity to do so. For all of the active schedules, there was hardly any difference noticeable. So from the occupant point of view, first lesson is it doesn't seem to really matter when you charge, what power level you charge. They will experience the same kind of degrees of comfort. So that was one finding, and this goes for the leaky house as much as for anything else. The second thing we looked at was do the different schedules mean that the occupants can have some kind of penalty, so they are forced to use more energy than they would otherwise. And so we looked at the total energy used between January and April. So we ran the simulation for 4 months, and we compared that to how well the devices were following the schedule that they were instructed to do. And once again, you'll see that nearly all of the schedules that we tested fell within a very, very tight band up here. So all the active schedules ended up with roughly the same behavior from the point of view of controllability, and the biggest total consumption difference was 7% more or less than the best case. So this technology allows the customers to use less energy than the teleswitching, and it allows the utility more. It gives it a better confidence that the instructions will be followed. These two red triangles represent the various versions of the teleswitching schedule that we applied. So far so good. There are some secondary lessons from the simulation outcomes. So there's a little bit of an influence of the time of day. These charts show 4 different schedules, and the green bars show times when the heaters were charging outside of instruction, and the brown bars show when they were charging to instruction, and the time of day is the horizontal axis, and then each day of the year is on the vertical axis. And so it is a little bit better if the power is delivered earlier in the day and at a low rather than high power level, but it's a small difference, and it's something that probably could be handled via either changes in tariff or some slight changes in schedule forecasting. It does require a reasonable 24-hour ahead demand forecast for each house, however. I think in the interest of time we'll pass over this one quite quickly, because we also built a forecaster that was capable of sort of coming up with a 24-hour ahead demand profile for not just one house but the whole estate of houses that was planned to be run, and come up with a 24-hour ahead demand forecast given the expected temperature next day. And this 24-hour demand forecast then is what we pass to the network modelers, so that they could look at the active network demand. And I'll hand you over to Simon now to talk about taking this to the next stage.
Thank you. Right, I'm going to try and go through the network modelling, probably in about 10 minutes or so, just to give you an idea of how long we'll go on for. if I skip over any slides quickly in the interest of time, I'm sure they'll be available online afterwards, and you're more than welcome to get in touch to ask any questions. So from a power system perspective, I think studying power systems allows you to ask the question of why, sort of the overall reason for why we're doing this. We live in a society which uses quite a lot of energy, and a lot of the pressure on us at the moment is to think about reducing energy usage or decarbonising energy usage. And the power system, the electrical power system, is one way in which we can do that. So the traditional way of managing a distribution network, that's the low voltage part of the electricity network that comes into your houses, your offices, etc., is to do it in a very static way. You do lots of studies when you set the system up, you connect generation to it, but you only connect enough generation so that it can operate under all circumstances, excluding some fault circumstances, but under all normal operating conditions you can allow your wind generation that's connected at distribution level, your solar generation, your biomass plants, whatever it is, to operate as they want without you, the network operator, doing anything about it. Now that means that a lot of the time there's more network capacity available than is being used, because you've sized your system for the worst case conditions, whatever those worst case conditions are, so that you don't have to manage it at all or communicate with what's on your network. Now that's changing now. The first scheme to really do it was on Orkney Islands, a wee bit south of Shetland, where there was a management of the power flow along the cables linking Orkney to the mainland UK. It's expensive to fit undersea electrical cables, but the worst case condition on Orkney meant that if there was low demand on Orkney, maximum wind generation, they'd run out of space in those conditions to fit any more wind. So what they decided to do was to fit a communications and control infrastructure called active network management. Any new wind that connected knew that it would have to be curtailed under certain circumstances, and they agreed to that as the condition for being able to get a network connection at all. Now that has allowed a significantly larger capacity of wind generation to connect to Orkney without really expensive upgrades of the undersea cables. It's allowed Orkney to be more renewable, to make more use of its fantastic renewable resources, and to make better use of the network infrastructure that's there. Now the same sort of thing is happening on Shetland. What we try and do when we run a power system is we think about maybe the energy trilemma, it's known as. We're trying to meet our energy needs whilst reducing emissions, minimising the costs, particularly in terms of things like fuel poverty for those on low incomes, and to manage the system and make sure it's secure, both secure in terms of the day-to-day operation and longer term in terms of security of supply of energy. But those three factors which apply to the energy system as a whole also apply specifically to Shetland. So minimising emissions involves connecting more renewable generation. That's one way of doing it. Managing demand within that as well is another way. I'll come on to that in a second. On Shetland, as with Orkney, the network operator identified the worst case conditions and only allowed 4 megawatts of wind generation to connect. Connecting more requires this communications and control infrastructure known as active network management. So connecting renewables reduces your emissions, and it can reduce the cost of supply, but installing active network management is a necessity if you do that to operate the system securely. And as part of that process you need to define what is meant by security of supply. That right hand side is effectively what Orkney did and what other active network management schemes are doing. But as soon as you ask wind generation to curtail to reduce its output, you then have an opportunity to try to use more of that potential generation within the constraints that you sit within. And that's where flexible demand, energy storage, frequency responsive demand on Shetland all come into play. And the left hand side of this diagram talks a little bit about that. Managing demand in line with wind generation, minimising peak electrical demand, making use of electrical storage. Now, this graph here you'll recognise from Katty's last slide. It's an example of the underlying demand for heat within a group of houses in Shetland across one day. There's a peak in the morning when people get up, and it's generally higher during the day than at night. That's something that makes sense. Now, that has been managed for the last 20 years or so on Shetland using teleswitching, as I'm sure many of you are aware of. Teleswitching allows you to fix when storage devices can charge within certain parts of the day. But on Shetland, and I think in most places that it's used in the UK, that schedule is fixed, so it operates the same schedule every day. That's good for managing variations in demand, because demand variations are fairly reliable. There's always a morning peak, there's always an evening peak, it's always a low demand overnight. So that's what's been done on Shetland for quite a long time. But when you have an excess of wind generation and you're trying to manage the variability of wind, that's unique every day. You can't define a time of day when it's always windy and it's not always windy. At least you can't do that in the UK. So that's where unique schedules made up every day based on what you expect to happen over the coming 24 hours are required. And that's part of what the power system sort of centralised intelligence has tried to do. What it tries to do is to take forecasts of demand, take forecasts of wind generation for the coming 24 hours, and use those to build a schedule which it then sends out to individual houses, which then attempt to implement that schedule. Now, that schedule doesn't always get implemented, because it's also important, and in some ways more important, to make sure that you meet customer expectations. Now, that's in terms of keeping the temperature in the houses at what people expect, making sure that they get what energy they need, and so those often take priority over the power system. But there's an interesting kind of combination of the two that we try and use there. So coming back onto the power system side, this is what the Shetland network really looked like before Nines. You had over here where it says firm generation. That means generation that is allowed to connect and generate at all times. Okay, it's the traditional way of managing the network. Okay, but what we've tried to do is move towards a new situation where we get more wind connected and we monitor the network all the time, and we have a control infrastructure which decides when to curtail certain generators in that non-firm set. So anything that's a little M on the diagram represents a measurement point, and it all feeds into the A&M system where there's a centralised controller sat in the middle. Now, as I said before, to operate a A&M situation, you need to define what the limits of wind generation are. And on Shetland, it's to do with frequency. So one of the issues with wind generation, particularly, it's called distributed wind generation because it's connected to a distribution network, and there's certain prerequisites in terms of protecting the network and the generation. So in the event of a fault, distributed generation such as this wind will disconnect from the network, and that can lead to an instantaneous loss of generation. That instantaneous loss of generation leads to a variation in the frequency, and there's an obligation on the system operator to maintain frequency within set limits. What you can see on this diagram here is the effect of losing a certain quantity of generation on the system frequency. So you can see just here the step change when the generation is lost, frequency drops, and then recovers as the remaining generation responds to that frequency change and ups its own output. As you increase the level of generation lost, i.e. the quantity of wind on the network that's disconnected, that minimum frequency drops. And when you reach 2% of nominal, i.e. the difference between where you started and where you finished was 2% of 50 hertz. That's as much wind generation as you allow on for that particular network situation. So what we did was run lots of models of all the viable network situations that might happen, and for each one of those we could then define, for this situation, which you can tell from the monitoring equipment, this is how much wind to go on. From that you build up what's shown here as a stable envelope for wind generation. Along the bottom is the total electrical demand, up the side is the total wind generation, and you must sit within the grey area at all times. Okay? That red dashed line marks the frequency limit. There are other limits in there as well, but remember that red line, because I'll come back to that in a slide or two. Let's put that away for now. Okay, so this is a network diagram of Shetland. I'll not show it for too long. If you're interested, you can have a look at it offline, because it shows you where all the various components fit within Shetland, and if you know the area, you can see from the names of the system buses where they're located on the islands. But basically, that's what we're trying to manage. The non-firm wind generation connected to the island, and then we're trying to manage flexible demand in line with when we expect that to be curtailed. So, the active network management system, I've actually talked about quite a few areas of this already. The left-hand box is the scheduling engine. That creates a 24-hour ahead schedule for the demand-side managed heaters. That schedule is then sent out and applied in real time. Obviously, conditions don't always develop as forecast. Wind forecasts aren't always accurate. Sometimes they're wrong. And if that happens, if there's a change from what's forecast, it's fine, because the system is monitoring the network in real time. It's monitoring what's actually happening, not what was predicted to happen. And if that means that you need to curtail wind more than you expected, it will do so because it needs to do that to maintain the system security. It can't allow extra wind on because maybe it's more windy than the forecast said. So the system is always secure, and you're trying to make that schedule as good as possible to get the most benefit out of the flexible demand. So here's just one day's example. For a given capacity of wind generation, the grey line in the top graph shows you what could have been generated. Okay, that was what was available through the wind resource. With no flexible demand, the red line shows you the level that's allowed for system stability reasons to connect. So it's significantly lower. Then you allow, I think in this case we ran 1,750 houses modelled with DDSM electric heating, and we said, how much curtailment can you remove? The green line shows the new wind generation, and the grey shaded area is therefore the additional wind generation that was allowed on because of DDSM that day. Okay, and then the bottom graph shows you how much DDSM is scheduled. Just to return to the idea of frequency stability, when I talked about the fact that when you have a mismatch of generation and demand, too much demand, too little generation, and your frequency starts to drop. This is where the frequency responsive component comes in. You set up a response within the heaters to the frequency. They measure that themselves, so this is independent of whatever's been scheduled to happen. Okay, if the frequency drops below, say, 49.5 Hertz, you then enter a droop curve region where the heater begins to reduce its output. And in this example here, when the frequency gets down to 49 Hertz, the heaters are completely off. That means that you have you've responded to that frequency response. Reduced demand in terms of frequency is the same as increased generation, and so that support allows you to actually fit more wind on and support the frequency, because you know you have that situation. There's the that stability graph that we talked about before, and with frequency responsive demand, the red line can increase, can rise up. Okay, so running some simulations, I'll not go through the details, but just to give you an idea of what you can achieve by this, I've shown the capacity factor of each additional megawatt of wind generation connected to the Shetland network. If there's no curtailment, in the year we chose, it had a capacity factor of about 0.45. Okay, as you connect a little bit of new wind, there's very little curtailment. Now, follow the blue line on that graph, the lowest one. As you start getting above 5 megawatts, the capacity factor drops off because more and more wind is curtailed. taking as a very hand-wavy kind of way of measuring the capacity factor that's needed before you have a viable wind project, then the UK average is approximately 0.25, so the black dashed line is an indication of what might be viable. And the blue line and the black dashed line intersect at about 14 megawatts. So that's how much, in our simulated case, how much is viable. Now add the flexible demand on, and you move up to the orange line. Between the area between the blue line and the orange line is the increased generation, and the distance between where the blue and the orange line intersect the black line, that represents how much additional capacity might be viable because you have flexible demand. So in this case, I mean, without being too precise, because this isn't a precise science in the real world, you might get an extra megawatt-ish to connect. Now turn the frequency response on, and on Shetland you get a big jump. With frequency response you reach the top line, and you may get an extra 2.5 megawatts approximately of wind generation that is viable on Shetland. Now that on Shetland is several percentage of the total electricity demand in Shetland per year that you're now able to meet through renewable generation as opposed to fossil fuel generation. And finally, just to pull that back to the UK mainland, on the UK mainland we have a much bigger system, but we still need frequency response, and that's almost always provided by generation. But through a system like this, an aggregation, a big group of houses, maybe all the houses in a certain town, could club together and offer frequency response service to National Grid, that's the UK system operator. The system operator pays for that, and that money could then be distributed among the consumers themselves as a way to reduce bills for mainland customers as well. So it's a really interesting topic, I think. So that's the end of my section. So I think we just have a couple of conclusion slides.
Yes, just to recap on what we've been talking about today. Decarbonising the electricity network will require a higher proportion of renewable generation, and that'll require storage, and the new generation electric storage heaters can provide significant cost-effective controllable distributed storage across Europe. Field trials of this technology show that they'll work without impacting customer comfort, although we have to remember that customers don't always use the technology as we expect, and that the storage heaters can provide flexible demand and storage for excess wind over a period of 1 to 2 days, and even over 2 days there seems to be no impact on either customer bills or comfort levels. And that we can also say that using simulation is a good means of exploring these new operational options without risking too much in the real environment. Oops.
Okay, and just my conclusions from the power system side. Shetland really is a pretty advanced smart grid. In terms of the UK, I would say by the end of this year, with everything that's rolling out on Shetland, it's probably the most advanced smart grid in the UK. And that's being driven by the sort of peculiarities of Shetland, but the learning that's being, that we'll take from there is going to be applied across all distribution networks in the UK. And I'll just say on that, there's 14 distribution networks in the UK, or 14 distribution network areas. All 14 in their business plans for the period 2015 to 2022 mention active network management as something that they're going to include on their network. Flexible storage is important. It helps manage the peak load, it helps increase generation once you have curtailment of wind, and therefore it can allow cheaper bills to customers if that link can be made across the network, and the frequency response component is very valuable as well. It does need good day ahead forecasting of wind and demand, and that is something that will be an ongoing I think research topic in this area, and to do that, to improve those forecasting techniques, we need as much data as we can get hold of, both in terms of demand, wind generation, forecasts of wind, forecasts of demand, and we need to sort of look at those both electrical engineering side and linking with the mechanical engineering side. Okay. Thank you.
Thank you very much. And we have some interesting questions from our online viewers. Some are just clarifications, some maybe you have already answered, but let's go through all of them. Starting with a very simple question about vocabulary, granularity. What is that? That's something you mentioned at the start of your presentation, Katalin.
Yes, I did use that word in connection with how the new heater technology being able to take in instructions for charging at a greater level of granularity. What I meant by that was a combination of short time steps, so that the heaters can change their power level every 15 minutes. They can switch to a different power setting, and also they have different power levels to switch between. So whereas under the old teleswitching arrangements with the old heaters, you were either off or you were on, and that was for a long block of time, you can now be off again, on again, off again, switch up, switch down every 15 minutes.
Okay. Next question. How do you propose to tackle the problem of self-synchronization and therefore oscillation if the heaters switch on-off based on frequency?
Okay, so we've done quite a lot of modelling of the dynamics of the system on Shetland. We've used quite complex dynamic simulation studies. With the current rollout, it's not an issue because it's a relatively small part of demand. As that kind of frequency responsive demand increased, you would need to be quite careful how you managed it. You would need to work closely with control engineers to see how the interaction of the demand response to frequency interacted with the response of generators through their governors and through their control systems. Through the use of like the deadband and the droop curve that I showed in one of the last graphs, you can make sure that you don't get the oscillations happening, maybe by delaying heaters coming back on by up to a minute or so, which is more than long enough for a frequency deviation on Shetland to have sort of smoothed itself out and the system to have returned to normal, or slowly bringing things back on rather than just turning everything back on at the same time.
Okay, the next one. Do you know the annual space heating and hot water demand at kilowatt hour per square meter of the monitor dwellings? So, annual.
Yes, I do, but I don't have the detailed information with me. What I can say is that the very highly insulated houses had a demand of something like 50 kilowatt hours per meter squared per year for heating. And the stone flat had about double that in terms of per meter.
Mm-hmm. Next question. Can this be applied to an urban area? And I think that was mentioned that this is applicable.
To do that?
Yeah.
Well, yes. In fact, in a place like Glasgow, there are, which is on a gas network, there are still significant parts of the city where they're using storage heating as a sort of cheap form of electric heating in high rises and sort of very, very sort of highly built over areas. And there is no reason why this technology couldn't work in that context. Dimplex have actually built these heaters to operate on a standalone basis, so their controllers can manage the heat input for a user without being connected into an active network management system. So they're available now, and I'm sure Dimplex would be very happy if they had some inquiries as to buying some. But they also have this other capacity, and yes, that could be applied anywhere.
A question that is really for SEC. I don't know if you will be able to answer, but let's see. Will SEC look to install these heaters oversized for storage capacity, for storage capacity, be free to the homeowner and see at a tariff comparable to main gas?
Okay, so one thing I should clarify here: it's not SSE who installed the heaters. It was a Shetland Housing Association that installed the heaters because it's their houses. And SSE Power Distribution Networks does not get involved in selling electricity or setting tariffs or anything like that. So if the question is, would there be in some future world some commercial arrangement that allowed people, either homeowners or housing associations, to buy oversized heaters to install because they get a better tariff for allowing their heaters to be used? I think that's entirely possible, but it will require a lot of cooperation from energy retailers and homeowners and network operators to actually make this happen. And of course, we're in a regulated environment, so at the end, Ofgem would have to approve all these arrangements. So we're some way from that point yet, because we're only, the SSE is only just proving that this system can work at the moment. But that maybe is the future.
Yeah, and I think I'm speaking for myself, not for SSE PD at all. But I think it's quite important that supply companies do start to think about how tariff arrangements can be made to sort of suit these sorts of things. As I said, basically when you're a generator and you're curtailed, you have the ability to generate, but there's no value in that because you can't export it. You're not allowed to do so. The cost of generating it once you've built your infrastructure is relatively small, so you should be prepared to accept a relatively small payment to generate. And again, customers, if they're going to provide flexibility, need to be reimbursed for that. They need to get some benefits. So, but there's definitely the ability to link there under some kind of localized energy system. And I really do hope that supply companies start to look at those options. And there needs to be encouragement, I would say, from the regulation and the government and the policy environment to make sure that happens.
Okay, thank you. What is the temperature range that storage heaters operate? Do you know if there is a technology for energy storage coolers that could be applied in warmer climates?
Right, so these heaters operate, the core temperature can go up to about 620 degrees centigrade. And at that temperature, you can still touch the outside surface without burning yourself. So they are pretty efficient in terms of how much energy they store in the space. For coolers, my honest answer is I don't know. I'm sure that there must be some sort of comparable technology for coolers, but I'm just not aware of that myself. Sorry.
Okay. Our next question. Did you model the turbines providing frequency response services into the network?
No, we didn't. It's quite easy there's the potential there, quite obviously, for wind generation to reduce its output if frequency rises too much, and the ability for turbines to do that is there. But to operate a wind turbine so that you can provide the increase in generation needed in the cases that we're talking about here, you would have to be operating your wind turbine below what it could actually achieve at that point in time. And that's not something that the operators are so keen on. But there is modelling happening elsewhere looking at those potentials, but it's more, I suppose, academic, I think, than looking at being rolled out just at the moment.
You mentioned mass heat storage facilities for district heating system. Has that happened yet?
Okay, so in Shetland, one of the things that is already installed in the capital, Lerwick, is a district heating system based on incineration of waste. They actually dispose of not just Shetland but all of Orkney's waste as well, and then they turn that into heat, and they have a network of pipes that go around the city and deliver heat into people's houses. But now that is operating at full capacity. So part of the 9 solution was to build an additional hot water tank for the existing district heating system, and have that powered by excess wind, and there would be a dedicated wind farm for it. That is one of the projects that's sort of being developed at the moment. So it's not starting a whole new district heating system, but it's expanding the capacity of something that exists.
Has any work been done in combining these heating systems to properties with heating, ventilation, air conditioning systems?
Yeah, I mean, air conditioning isn't really a big requirement in Shetland. In terms of this project, no. It is something that could be done. It wouldn't take a lot to expand the simulation models into looking at larger buildings and sort of HVAC serviced buildings. But at the moment, we've just been looking at domestic scale properties in the north.
How effectively could this model be used to free up the current constraints in the Orkney grid, where SSE declared a moratorium on new onshore wind in September 2012, and where some turbines are so heavily constrained that they are becoming financially unviable?
There's general learning, I think, that can come out of this that can be applied to Orkney. In terms of how you control a system, how you link demand flexibility to wind turbine curtailments, and that's what the Shetland system is doing. I know a little bit about the issues that are happening on Orkney, and my feeling is that I think it's probably the supply company side that needs to be developed, in terms of making sure that there's ways that fit within the regulation that allow a company to buy and sell electricity locally, and then to make sure that the distribution network operator can allow that. These sorts of things are physically and engineeringly possible, but there's a difference between that and persuading a distribution network operator to change their policy, when a change in policy can affect other users of the network. And also, they're rightly quite conservative because they have to keep the lights on to everyone, and they don't want to put that in jeopardy, I suppose.
Were there any special tariffs offered to the users for using the power at convenience of the power system?
So one of the specific rules that Ofgem set around the ninth trial was that it had to stay within the existing tariff arrangements. Now, Shetland has some specific Shetland tariffs that have existed there, which allow a greater range of timings for teleswitching than the traditional Economy 7 or Economy 10 tariffs on the mainland. But even so, the timing had to fit within the existing tariffs. I think part of the going forward work will be to look at exploring and justifying different arrangements. So that's the next step.
A question about materials. What material is used in the electric heaters to store the heat, if that can be disclosed?
It's magnetite is predominantly what it's made of, which is a compound of iron 3 oxide compound. But it's magnetite that's specially milled, rolled, crushed, compressed and processed to have at the same time a very high heat capacity and also quite a high sort of heat conductivity within the magnetite, because ceramic materials tend to not be that conductive. So the absolute details of the material that make up the core do tend to be not published, but that's roughly what it is.
Is Iceland Housing Association specifically addressing the issue of residents fiddling with the controls and so confusing the heaters? This would be a concern for any housing association considering mass installation.
Absolutely. They've during the rollout, having learned from the Sixth House trial, they've put in massive extra efforts into producing really simple to use guidelines, to going and giving each household some basic training on how to use the controls, and they still have the dedicated housing officer to answer questions. But that said, there's nothing that makes people read instructions, and tenants will change anyway. So yes, so it's going to be an ongoing challenge.
Okay, well, we do not have any more questions and we have run out of time. So I would like to thank you very much for the excellent presentation and to thank you, our online viewers, for all the questions. And I just wanted to draw attention of our online viewers two events, well, one webinar and one event that we are preparing. On 25th of March, there will be a webinar entitled Towards Community Energy Solutions in Lithgow, and we will have speakers from Transition Lithgow, from University of Aberdeen and University of Aberdeen in Dundee. And on 31st of March, we have a live event here in Glasgow in the Lighthouse. That will not be a webinar, it will not be filmed, but for those who can attend, participate in this event, it is about integration of low-carbon infrastructure in the built environment. And the event will provide an overview of our current project, of our planned collaboration in future with further education colleges. And we will have a workshop with further education colleges to explore how they would like to engage with our project. Regarding the webinar on 25th of March, please book a place online, and thank you very much for watching this webinar. Thank you.